Physicist and author Lawrence Krauss to get his take on the latest scientific news, ideas, and theories. And among the topics on the table for this edition, why antimatter matters.
It's great to be back.
I've got all sorts of questions. Let's start with something easy.
Oh, sure.
What is matter? What is antimatter? And when do the twain ever meet?
Well, you know, antimatter really isn't as strange. It sounds like a science fiction concept, and it is used in science fiction, in Star Trek and everything else, but it's really not that strange. It's strange in the sense that Belgians are strange. And what I mean by that is you go in a big room and ask how many Belgians there are, you won't see many. But you go to Belgium, they're pretty normal people. And so the reason antimatter seems so strange is that we happen to live in a universe of matter. But antimatter is just for every particle in nature. The laws of relativity and quantum mechanics tell us that for every particle, there should be a particle of equal mass but opposite electric charge, basically. So a proton has an antiproton. Same mass, opposite electric charge. An electron has an anti-electron. We call it the positron. And when these were first proposed, it was outlandish, but in fact, it was true. In fact, Dirac, who first proposed antiparticles, didn't believe in them. And then later on, he said his equations were smarter than he was. But the thing about matter and antimatter that makes it kind of exciting and exotic is that you put matter and antimatter together, a proton and antiproton, they can annihilate into pure radiation.
Okay, why does that happen? Why do they annihilate each other?
Well, because it's possible, because they have opposite charges, and therefore, in quantum mechanics, anything that's possible happens, and mass can turn into energy. And if you have a positive charge and a negative charge, the sum total charge is zero. So you can create pure energy since you don't have any electric charge left. Quantum mechanics allows that to happen. You can't take two positively charged particles and annihilate them purely into radiation because you have some charge. Similarly, you can't take a proton and an electron and annihilate them because they have very different mass. You need exactly the same mass to annihilate.
Okay.
And the big question, and the thing that you probably wake up every morning and ask yourself is, why do we live in a universe full of matter and not antimatter?
Boy, you and me both, huh?
And you should, because it's really remarkable. If you were a sensible creator, you'd create a universe with equal amounts of matter and antimatter because they have the same mass. And if you dump a lot of energy in the universe, heat it up, you'll produce equal amounts of particles and antiparticles. And so what's really weird is when we look out at the galaxies, we only see matter and no antimatter. The antimatter we create in laboratories. We can do that by collisions. And so we think, and one of the great sort of unheralded developments in theoretical physics is a way of trying to understand how you might start out with a universe that had equal amounts of matter and antimatter and end up with the universe that we live in. If it wasn't the case, the universe would be pretty boring. We wouldn't be having this conversation because if you had equal amounts of matter and antimatter, they'd all annihilate and you'd have nothing left in the universe. But it turns out we think that through processes we can sort of understand for every billion particles of antimatter in the universe, 1,000,000,001 particles of matter were made. And so the billion particles of matter and the billion particles of antimatter are annihilated, and that actually produces the cosmic microwave background radiation that we see. There are 1 billion photons in the cosmic microwave background for each proton in the universe, but that one extra particle of matter didn't have any particles of antimatter to annihilate with, and it got left over. And if you do that in every region of space, you end up with enough matter to account for everything we see.
And that's what we have.
That's what we have. Now, that's a theory. The neat thing would be to test that theory. Right?
Yes.
And you have to have some process that creates, it starts out with equal amounts of matter and antimatter and creates the matter. Well, physics is a two-way street. So if you can create matter where there was none before, you should be able to destroy it. And the prediction of this theory is that diamonds are not eternal. That if you take a proton, like the protons that make up the particles in this table, if you wait long enough, they'll decay. They'll decay and disappear. You have to wait a long time.
Yes.
We think about 10 to the 35 years, which is about 1 billion, billion, billion times the age of the universe almost. And you might say, well, how can you test that? Quantum mechanics again, because if you get 10 to the 35 protons in a single place, on average, one will decay each year. And we have big, big tanks of water underground in Japan and other places, 50,000 tons of water, instrumented with phototubes, sitting in there in the dark to wait and see if any protons decay. They haven't decayed yet, but we're still waiting.
There's still time to wait, I guess. Yeah.
And if we do understand that, we'll understand why we're here. We'll understand the process that led to a universe full of matter as I say, otherwise it'd be a beautiful universe. There'd be nothing in it. It'd be quite elegant, but it wouldn't be as much fun.
Okay, obviously quantum mechanics is involved there. There's something called quantum teleportation, where a recent experiment, some sort of deal here over in the Canary Islands somewhere, 143 kilometers, a new record for what?
For what? Well, it sounds, the point is if you say teleportation, you immediately get in the newspapers. But quantum teleportation is in principle just like the transporter on Star Trek again. And I keep mentioning Star Trek. Maybe I'm contractually obliged. I don't know. But in Star Trek, remember, you have Spock or Kirk or whoever, and they get destroyed right here, and then suddenly they reappear on the planet. Now, it would be wonderful. I travel a tremendous amount. I'm going to Europe on the weekend. I would love to have a transporter, but you can't. But you can do it for atoms or quantum mechanical objects. You and I aren't quantum mechanical. We're very classical. But it turns out it is possible if you very carefully prepare some quantum mechanical states, like photons, the particles in that experiment, very carefully prepare them in the laboratory and let them travel off in different directions. They are intimately connected in a way that's completely impossible to imagine classically. If I measure this particle here, I make a measurement on it, it instantaneously affects the state of that particle over there, even if it's on the other side of the galaxy. Einstein hated it. He called it spooky action at a distance. He didn't like it. It's a property of quantum mechanics, and it's true, and we can test it. And one of the ways we can test it is by very carefully preparing these states, making sure they don't interact with anything on the way. And then if you do things just right in the laboratory, you can literally destroy this particle, the quantum mechanical state of this particle, and instantaneously recreate the quantum mechanical state of that particle over here. Instantaneously, no time difference, and that's what they were able to do over 143 kilometers. It's not the other side of the galaxy, but it demonstrates this spooky action at a distance really works. And it's fascinating. It would be very useful in principle if we could do it, obviously. It turns out you can't send information from one place to another faster than light. It's a little too long to describe here, but even though it sounds like information is traveling faster than light, it turns out there's no message you can create here that would end up over here faster than light.
But it would be faster than what we have, wouldn't it? I mean, could you talk about quantum computers here, quantum
the point
internet?
is, if you use that weird property of quantum mechanics and made a computer using that weird property, then using some complementary properties of quantum mechanics, you could actually make extremely fast computers. Quantum computers that could operate almost infinitely faster than the classical computers. But the nice thing you could also do is if you could do this, if you could prepare these states, even though you couldn't transfer information faster than light, if you could keep them entangled, quantum mechanically entangled, then you could have secure messaging. Because it turns out, in looking at the properties of this particle, you would know if the other particle had been tampered with. So you can make completely secure communication. And so if you're worried about being intercepted by spies or whatever, you can be completely secure. That's the good news. The good news is quantum teleportation could lead to completely secure messaging. The bad news is if you could make quantum computers, which isn't so bad, we'd be able to do a lot of things we can't do now. You'd probably be able to, it turns out, decode all the information in your credit cards and that the bank used to store your information in a finite amount of time, so all our credit cards would suddenly be insecure. So you can decide which you like better.
It's a hacker's paradise.
It's a hacker's paradise. And so like all things in technology, there's good sides and bad sides. You got to be prepared for them.
You mentioned, okay, a little split here. So there's a symbiotic relationship, if I may be so bold, between these two particular particles.
They're intimately connected,
okay,
even though they're very far away.
But they're far away, but it sounded like you said as long as the space between them is what? Smooth, free, non-interactive?
As long as they don't interact with the air and other people and other particles so that their quantum mechanical state isn't destroyed on the way, as long as they're pristine, then it works.
How do you ensure that?
Well, one of the ways you can do that is the simplest way is to put them in a vacuum so they're not interacting. Other ways is you can use frequencies of lights that you can be relatively sure can travel through the atmosphere without a single interaction. You know, we can see light from the sun. It makes it to us through the atmosphere. If it interacted a lot, it wouldn't get to us. In fact, that's, as you may know, why it's red at sunset and blue during the day, because certain light gets scattered down and certain light doesn't. And so if the blue light gets scattered away, the red light comes to you. So if you use frequencies of light that can that can make, or microwaves or radio waves that can make it through the atmosphere without interaction, then you're okay.
And is that relatively easy to do? Can you do like satellite? Can this be satellite technology in the future?
I could definitely imagine this kind of thing being used for satellite technology in the future, yeah.
Before we go, we've talked a lot about quantum mechanics, and obviously, goodness gracious, it can be so confusing because it doesn't seem to make much.
No one understands quantum mechanics. We just use it.
Okay, well, and there you go. I mean, there it is. There you are, and there.
The equations are smarter than we are.
But give us a quick explanation here, as quick as you can.
Oh, as quick as I can.
Yeah,
okay.
Of everything we've talked about here, it deals with quantum mechanics. Okay, what are we talking about?
Well, quantum mechanics really says that at a fundamental level, the universe is very different than we see. In fact, at a fundamental scale, what quantum mechanics says is that objects are doing many things at the same time. That's the weirdness of quantum mechanics. There's many different ways of thinking about it, but Richard Feynman, who I wrote a book about, really demonstrated that that's the heart of quantum mechanics. If I take a baseball and throw it to you, it'll take some trajectory. But if I take an electron and move it from here to there, it turns out it doesn't take a single trajectory. It takes every trajectory. It goes to the moon and back. And in fact, the probability that it'll end up at your position, if it starts out in my position, requires you to sum over all the possible paths an electron could take. It's doing many things at the same time. An electron is spinning, for example, but it turns out, so we can measure an electron spinning in a certain direction, but it turns out before we made the measurement, it's spinning in all directions at the same time. It sounds crazy. It's completely impossible for us to visualize, and part of the reason is, as my friend Richard Dawkins was saying the other day when I was talking to him, we evolved to avoid tigers in the wild. We didn't evolve to do quantum mechanics, so our brains, visually can't understand this kind of behavior. It's amazing that with our experiments and our theory, we've been able to deduce that it happens and use it. The semiconductors in my computer depend on that weird behavior all the time.
So if all things are possible, is it possible for me to put my hand through this desk? At some point in the history of all time and energy, am I going to be able to put my hand through this desk?
Maybe. The answer is maybe, in the sense that effectively no, because you are very classical. If you were like an electron, you could run from here towards the wall at the end of the room head first. I suggest you try right after we talk, as fast as you can, and if you did it enough times, you disappear at this end and appear on the other side of the wall. Electrons do it. It's called tunneling. But we're so classical, such big objects, that the rules of quantum mechanics get all washed out, and we behave quite classically. So while there's a non-zero possibility that your hand could go through this table, the probability is so small that you could do it from now probably till all the stars in the universe burn out, and all you'd have is a very sore hand.
All right. I think I understand that and probably don't. Next time we talk, I want to talk about this business about gamma rays 7 billion light years away. They wind up on our shores, and it looks like they didn't disperse hardly at all. Nothing happened out there.
Yeah, we can talk about that because it's kind of interesting because it tells us something about the properties of space and time.
All right, we'll do that next.